Alright, welcome back to another video by Firestarter Graphics and Engineering. Today we're going to talk about another type of simulation that we can do for our rockets. Now we just spent a lot of time doing some computational fluid dynamics with rockets and then comparing those values to OpenRocket that uses the Barman equations and some other equations that we went over last time. So what could we do that's going to be any different? Well, last time you noticed that our coefficient of drag varied just a little bit between computational fluid dynamics and OpenRocket using those equations. So, and also if you did wind tunnel testing, there would be some variance. So what can we do with that variance? Well, there's plenty we can do. So let's first list what things can vary with a rocket. Well, we know the coefficient of drag can vary. We know the mass can vary. We know the thrust of the motor can vary, and let's see, air density can vary as we increase in altitude. If mass varies, then your weight will vary. And when I say mass and weight, I am differentiating between the two. Like mass is the total mass of the rocket, weight would be mass times gravity. So taking that into consideration. So what does that do for us? Well, if we run 1,000 simulations with all that variance, we can then graph what we call a histogram and see what the most common situation would be. So let's go ahead and do that. But first, we need some equations. So I'm going to go ahead and open up Google, and you're going to type in, what's it called? Just rocket mime space rocket equations, and you're going to hit the first page and it's going to take you here. It's going to say rocket equations, and then related pages. This all has some excellent information, but we want the first page. So when you click it, it's going to take you to here. Equations we want to mess with is K, which is what we call the dynamic viscosity. Other people call it beta. I'm used to calling it beta, but this is not dynamic viscosity, dynamic pressure. So you have your density, your coefficient of drag, area, and then you're dividing it by 2. This is your dynamic pressure. It's either labeled as K or beta, depending on which physics book you are using. Then we want to deal with Y1, which is our altitude at burnout, and then our coasting distance. And notice that each one of these deals with the natural log. Now, why would it have a natural log when we're used to seeing trajectory equations as quadratics? Well, that's because the mass is changing as it goes higher. The mass is lessening. So if you go to your favorite search engine and type in ideal rocket equation, go to the first hit through the NASA Glenn Research Center and take a peek at this right here. Your change in velocity is equal to the equivalent volume of, is V volume, capital V? Nope. They have, usually it's exhaust velocity for this one. They might have been a typo, but that's okay. Anyways, it's your exhaust velocity multiplied by the natural log of the mass of your fuel, of full versus mass of empty. This is called your propellant mass ratio. And so you can go ahead and follow this through if you want. And the last little part right here is nice to read. It kind of gives you an example of what the whole ideal rocket equation is about. And so, but you're probably asking now, wait a minute, what does velocity have to do with altitude? Well, in calculus, when you integrate acceleration, you get velocity. If you integrate velocity, you get position. So you're moving backwards to get an equation, a really complicated equation, down to an algebraic equation, something that we can work with. And that's pretty much the whole point of calculus, one of them. Anyway, okay, so at this point I use the window snipping tool, and I will copy the dynamic pressure, Y1 and YC, and paste them in Excel. And I'll show you that here in a minute. But first, let's do a couple tips and tricks. So if this was my trial number, okay, and this was starting at 1, and we wanted 1,000 simulations. If I just click 1 and then go underneath the column called editing, and then click this one called fill, and then go down to series, click columns, click 1000 and hit enter. It'll take you and just automatically fill all those down. Okay, perfect. So now another tip and trick, if you want to do equals 5 times this right here and hit enter, if we click on that, hit control copy or control C, scroll all the way down, then holding shift, click the last cell, it highlights everything, control V, it'll fill that entire equation in. So just a tip and trick there. Now if we wanted to go here and go equals 5 times, starting with this one and then times, but we want it to always multiply by B3. So for example, if I were to take this and scroll it down, notice that it goes B4 and then it just keeps increasing, but we don't want that. We want it to stay always B3. This is where you click your cursor there, hit a $sign, hit a $sign, and now if I drag it down, it's always going to be that same B3 value. So those are important because that's what we're going to use for this project. Okay, so I went ahead and opened up the Monte Carlo Simulations so that you can see. I'm not going to show step by step. I'll show you the formulas, but I'm not going to do everything step by step. So you saw how I did the trial number. So now let's look at the thrust. I have a normal distribution, some sort of random number, 550 and then 15. So what does this all mean? So I'm just going to click that and it shows us normal distribution, the probability, that's our random number, we want it to be random, and then we're multiplying that random number by the average and then adding in our standard deviation or variance of plus or minus 15 newtons. So normal distribution, why did we pick this versus any other distribution? Well, normal distribution means you have an equal chance to pick the same, so everything's symmetrically spaced, but you have an equal chance to pick one value over the other, versus a Weibel or a Weibel, however you pronounce his name. Everything is pointing to the far left or to the far right, it's skewed, and you don't want that. You don't want to pick higher numbers or lower numbers. You want it to have an equal chance across the board. Okay, so just use this formula, but put in the numbers that you want here, depending on what motor. I'm using an H550, so 550 makes sense. Hit escape, and then drag coefficient. So for my testing, it was between 0.5 and 0.4 with I'm doing a slight variance of, it's not going to go any higher than, it's adding 0.4 to it, that's what we're doing. Taking the random number, multiplying it between this value, and then adding 0.4 so that it's always above 0.4, if that makes sense. So let me say that again. Random number is being multiplied by 0.553 or something in between these two, and then you're adding 0.4 to it so that it's always above 0.4, but it's not going to be above 0.553, because if your highest random number is 1, then our highest value is 0.553 and our lowest is 0.456. Okay, then we'll do the same thing with our mass. It's a normal distribution again. Dynamic pressure, G2, which is our area, that stays constant. This is a perfect example of why we'd use the dollar signs or the string function. And then velocity is just a normal distribution of 203 meters per second with plus or minus of 2 meters per second. Whatever that random value is multiplied by the 203. That's why some of them 204, 198. Okay. Air density, for my location, is 1.1. Corrected air density is normal distribution, random, with a variance of 0.02. so that it changes, and then mass times gravity is just mass times gravity. Okay, so you can see my equations pasted here. And so what I did was look at max altitude, and I just filled in the equation for the coasting velocity. That is what max altitude is coasting velocity plus your burnout velocity. Now you'll notice my equation's a lot shorter than these two mixed together. That's because I went ahead and calculated the burnout velocity for my rocket, and its average was 75 meters. Now if you really wanted more accurate, you would do this equation in another column 1,000 times and then add them together. But mine was always averaging 74.98, so I just put it as 75, and that's where this came from. Okay, so that is the max altitude for the first simulation, and as I pasted it down, after 1,000 simulations, this is, that's what we end up with. And so dynamic pressure. Okay, so what do we do now? Well, if you click on E, or whatever column is your max altitude, it'll select the whole thing. And if you go to Insert, you can go to Statistical Charts, and you can do a histogram. And that's the one we're going to be looking at. But I've already done that. It's over here. So it looks like right now 708 meters per second is the most common. So most likely my current rocket would do 708 meters, times that by 3.28 to get feet. So roughly 2,100 feet or so. Speaking of that, I took my average max altitude and multiplied it by 3.28 so I could see it. Standard deviation, times it by 3.28, so I have plus or minus 91 feet. And that's it. So yeah, now that it reloaded, it looks like this common one is 704, and you're wondering, well, why is it changing? Well, every time you click on one of these that has the formula, since it's random, if you click out, it regenerates it. So just be mindful of that. So 722, that adds in another randomness to the entire situation. So you want to make sure that your values you're using isn't too far of a spread where it causes issues and skewness with the histogram. Anyways, I hope this made sense, and it's just another way to do statistical engineering analysis on something to kind of see the trends and what's going to happen with things. But yeah, thank you for watching, and I hope this helps.